Introduction to the Maclaurin series expansion. This is taken from the Core Pure 2 book, Chapter 2 for Edexcel Further Maths. The first thing to point out is that every function that you've come across so far, including many that you haven't, can be expanded in a way that so far you've probably only seen for binomial expansion. So in particular, cos x can be thought of as this expansion, 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and so on. This expansion, a lot like the Year 2 A-level Maths binomial expansions, goes on forever. You can see the animation showing how it gets increasingly good at approximating the curve, but it's never going to be quite perfect unless you somehow manage to include the entire infinite number of terms, which of course you can't do for any practical purposes when you're calculating, but it can be a really useful way of taking a function and sort of extracting what I like to call the DNA of the function, to try to find out exactly what it is going on behind the scenes and why the function behaves the way it does. Now, if you took part in the A-level Further Maths Taster Week that we did last year, then you might remember this process, but I'd like you, whether or not you did, to see if you can make use of calculus. If you know the derivatives or the integrals of sine or cos, see if you can make use of calculus to convert the expression that you're given here, the infinite expansion for cos, into a similar expansion for sine. Pause, give that a try, come back when you're ready to check your answers. Right, this is what you should have got. There's a couple of ways to do this. If you integrate cos x, you jump straight to sine x. So 1 can integrate to give you x, x squared over 2 integrates to give you x cubed over 6, and so on. You could also differentiate cos x, and if you do that, remember you'll end up with the negative of sine x. And then you just have to go through and change all the signs. It's worth noticing a couple of things at this point. The two expressions look similar. They've got a lot of related patterns going on. We've got factorials on the bottom that match the powers on the top, but you might also notice that the powers for cos are all even, the powers for sine are all odd. That fits with the concept of cos being an even function and sine being an odd function. You can tell from the graphs that are drawn that the functions have different symmetries. We've got the mirror symmetry of cos, and we've got rotational symmetry for sine. Those are the characteristic symmetries you would expect for an even function and an odd function, respectively. But there's more. We're going to investigate these expansions a little bit further, and then we're going to get into how you would construct them for yourself, how you derive them from first principles, and how you might derive similar expansions for more complicated functions or mixtures and combinations of other functions. So let's start by looking at another one, the series expansion for e to the x. If you've been playing with complex numbers recently, it will probably come as no surprise to discover that the DNA of e to the x and the DNA of sine x and cos x are suspiciously similar. It's like we've discovered some kind of missing link, hidden ancestor of these functions that previously wasn't obvious at all. What I'd like you to do is see if you can adapt this. To start with, we're going to substitute something imaginary into the expansion. So remember, whenever you've got an x on one side of an identity, you can replace that x with anything you like, as long as you replace x on both sides, everywhere where it appears, with the same thing. So have a go at replacing x with I theta, and then when you've done it, I'd like you to separate your infinite expansion into real and imaginary components. Use your own judgment as to how far along the expansion you go. You want to make sure you go far enough that you can see clearly the pattern and how it's going to continue, but don't keep going further and further just for the sake of it. When you've managed to split it into real and imaginary components, have a look, have a think, see if you notice anything special about it. Pause, have a go at that task, and then come back. Right, if we substitute I theta, the first thing you'll notice is you're going to get increasing powers of I popping out. But we already know, if you're familiar with imaginary numbers, the powers of I all reduce down to either I or 1, or minus 1, I suppose. So, although initially you'll get something like this, if we want to break this apart into real and imaginary components separately, we're going to have to evaluate and simplify those. I theta all squared, for instance, becomes minus 1 times theta squared. I cubed can be pulled out from I theta cubed, and I cubed is just I squared times I, which is minus 1 times I, and then I to the 4 is even simpler because I to the 4 is I squared squared, and I squared is minus 1, so I to the 4 is 1. When you've pulled all of that out, you'll realize that what the I has done for us is something rather special. For starters, it's managed to extract in real and imaginary parts the terms that have either an odd power or an even power. In addition to that, we've also managed to introduce an alternating sign situation. Now, I could have made alternating signs just by replacing x with negative x, and then every even power will come out positive, but every odd power will come out negative. What I wanted here was something more than that. I needed to replace x with something that, when it was evaluated, would not just give me alternating signs, but would also separate the even powers from the odd powers. So I've effectively got a cyclical process with 4 stages to it. So I need a positive real, followed by a positive imaginary, followed by a negative real, followed by a negative imaginary, and then back to positive real, positive imaginary, negative real, negative imaginary. If you think about it, you can visualize this as rotating around the Argand diagram. And when we extract those and pull apart the real and the imaginary bits, hopefully you've noticed this is identical to cos theta plus I times sine theta. The real bit is exactly cos theta, the imaginary bit is sine theta. And you might have been shown a different, either more efficient or messier looking proof of this particular relation. It's known as Euler's relation, but this is one of the most common ways that the relation is initially introduced or proved. So it's worth being aware of, and it's a nice little connection between the exponential function and the trig functions. For completeness, this is what the exponential curve looks like, and you'll notice that the graph is a very good fit as you go further and further along, but crucially, it's only going to be a particularly good fit close to when x is 0, and the further away you get from 0, the less accurate it becomes. There isn't actually a hard limit for e to the x in the way that there is for, say, year 2 binomial, where you've got negative or fractional powers. And in fact, there isn't a hard limit for sine or cos either. These expansions are valid for any value of x. However, they still have the property that they're going to be more accurate as estimates of the original function when x is close to 0. So if you're only going to look at the first 5 or 6 terms of an expansion, you can't realistically expect it to give you a good estimate for very large values, although it should still give you a good estimate for very small values. We're now going to look at how we can derive a formula. We've got to start by making one key assumption, and that is essentially that the function we're dealing with is one that can be accurately represented by a possibly infinite polynomial. Now, this is obviously true for polynomials, because beyond a certain point, you just have 0x to the 7, 0x to the 8, and so on. But it turns out it is also true for pretty much every other function that you've encountered, and every function that you will encounter later on in this course. Essentially, unless you do a bit of weird mucking about, you're going to find yourself in a situation where you can differentiate the function over and over again, which means you basically follow these steps. We're going to find the function and its derivative and its second derivative and its third derivative and so on as far as we need to. And then for each of those, we'll sub in 0 and we're going to get an additional bit of information. Before I show you, I want to talk to you briefly about what this is kind of telling you about the function. Imagine you're zooming in on the very beginning of the function, by which I mean what happens when x is 0. We'll think of these series as being centered at 0 because that's where the results will be the most accurate, when x is close to 0. And you'll look later on potentially at Taylor series, where you can center your function at any other point, which is essentially this, but translated across. But when they're centered at 0, we can think of the start of the function as having various interesting properties, and we can discover all of those properties just by zooming in further and further and looking more and more subtly. Property number 1 is where the function is, in other words, the y-intercept. Property number 2 is which way the function's going, so the gradient. And with just those 2 properties, you could create a straight line that passes through the same y-intercept and is tangent to the curve at that point. And that would be a Maclaurin series expansion that just has 2 terms, a constant and an x term. But you can go a level further and look at how the gradient's changing. In other words, what kind of curvature you're dealing with. Is it has it got a high second derivative, a low second derivative, a negative second derivative, etc. And that next bit of information will be enough to create a quadratic that matched the function perfectly at exactly its starting point, and then it would only diverge as you move further and further away from zero. Every new derivative you take gives you a more nuanced depiction of the function at that starting point, and therefore it's going to match the function better as you gradually move away from that starting point. It's like matching a car's position might only keep you level with the car for an instant if the car's going a very different speed. But if you also match speeds, then you'll continue in a similar position to the car for a bit longer. If you also match accelerations, then as the car speeds up, as time goes by, you will speed up at the same rate. And if you're completely matching location, speed, and acceleration at one particular instant, then you're likely to still be tracking the car pretty closely, even if you look ahead a few seconds into the future. The more derivatives you look at, the more closely you'll track for longer. Let's look at what it looks like in practice. We'll start with an assumption that the function can be written as an infinite polynomial, and we'll see why differentiating over and over again is useful for us. Firstly, what happens when we put in 0? Everything apart from the first term disappears. So if I know there is an infinite polynomial that matches, for instance, the cos graph, all I need to do to find the first term is say, well, cos of 0 is 1. So the y-intercept of my infinite polynomial is 1. So in this case, a equals 1. Then we go a step further. If we differentiate this infinite polynomial, we get another infinite polynomial. But now the a has disappeared, and the bx term has turned into b. So if we substitute 0 into this, if we know the derivative of cos is minus sine, I can now do minus sine of 0 and compare it to this expansion on the right, which is b plus a bunch of zeros. So minus sine of 0 must be equal to b. b must be minus sine of 0. And you can do this with literally any function. So I'll work through it with this general version, f, f dashed, f double dashed, and so on. And we'll derive from this a general formula, which you'll be pleased to hear is in the formula book, and you can just pull it out and use it whenever you need. So the beauty of this is that every time you differentiate, you're able to substitute in 0 and extract an additional piece of information, the value of a, b, c, d, e, and so on. When we sub in 0, we find there is a connection. It doesn't remain a direct connection. A is f of 0, b is f dashed of 0, but then 2c is f double dashed of 0. You can probably see why if you look carefully at the coefficients that are coming out as we differentiate over and over again. The 24, for instance, that comes out with the fourth derivative, you can trace it back from 24e all the way up 12e, 4e, e. It came from bringing the power of 4 down, and then the power of 3, then the power of 2, finally the power of 1, and that means it must be 4 times 3 times 2 times 1. That 24 is just 4 factorial. When we rearrange these just slightly, we can generate actual expressions for a, b, c, d, and e in terms of derivatives of the function evaluated at 0. And then we go back and we put it back into the first line with the a, b, c, d, e, and out pops the general formula, which, as I've said, is provided in the formula book. So if you want to find the Maclaurin series expansion for literally any function that you might care to deal with, as long as it has a valid Maclaurin series expansion, you can generate it like this. Just take repeated derivatives and sub in 0, and then use this formula. The formula takes care of the weird factorials, like the 2 factorial, 3 factorial, and so on, will correspond to the powers of x, just like they did in the sine and cos ones that we saw earlier, because sine and cos will evaluate to 0 or 1 or minus 1, depending on where you happen to be when you sub in 0, which is why that one matched so closely with this general formula. Have a go at using the formula now. You don't have to rederive from scratch, just apply the formula for these 3 examples. I suggest you start with e to the 2x. E to the 2x is your function. Try differentiating it over and over again, but then go back to each of your values, to the function, the derivative f dash, the second derivative f double dash, and so on, and sub in 0, and that will pull out for you the values that will form part of the coefficients of your general infinite polynomial. Pause Have a go at these three. In particular, I want you to be asking the question for the last one, why can't we use Maclaurin series expansion formula for just ln of x? Why did I have to make it awkward by going for ln of x plus 1? And another thing I want to draw your attention to before you begin is that I'm asking you for the first three non-zero terms. You might remember the sine and cos formulas only had even or only had odd powers of x. And that's because often when you sub in 0, you'll just get 0. And that's useful, but if you're asked to find an expansion, typically you'll be asked for the first few non-zero terms so that you've got to do enough work to actually produce a few values. So that might be a little harder for the sine squared. Pause, have a go at those, and then come back when you're ready. Let's take a look at the first example, e to the 2x. So the process is this three-step trick. Evaluate at x equals 0, differentiate, evaluate that at x equals 0, go back and differentiate again, evaluate that at x equals 0, and so on. F of x is e to the 2x. The derivative f dashed, 2e to the 2x, a bit of quick chain rule. Chain rule one more time for the second derivative, 4e to the 2x. You can sub in 0 to each of those, and you'll generate, pleasingly, all non-zero numbers, so we only need to go up to the second derivative here. The zeroth, first, and second derivatives is sufficient. Plug them into the formula, 1, 2, and 4, in place of f of 0, f dashed of 0, f double dashed of 0, and this is the beginning of our expansion. And that's it. For the second example, this will take a little bit more work, partly because sine squared x is messier to differentiate repeatedly, and partly because there's going to be a lot of zeros come out. But let's give it a try. We start by defining the function f of x equals sine squared x, and then we differentiate. We can use chain rule here, 2 lots of sine x multiplied by the derivative of sine x, 2 times sine x times cos x. And then if we want to jump ahead and differentiate again straight away, then we're going to need product rule, because we've got a sine times a cos. So it'll be 2 lots of sine x times the derivative of cos x, and then 2 lots of the derivative of sine x times cos x. The two can be kept outside if you like, and you can focus just on sine times cos using product rule. However you want to do it, you'll end up with something a bit like this. If you found a different way to do this, I'll come back to that in a second. You're not necessarily incorrect. You've probably found a slightly more efficient way than the one I'm demonstrating here. Now, I've differentiated a few additional times, because if you look at the expressions we've got so far, before we even write it down, we can tell what's going to happen when we substitute in x equals 0. Sine squared of 0 is 0. 2 sine 0 cos 0 is 0. So f of x and f dashed of x are both going to evaluate to 0. There won't be a constant term. There won't even be an x term. This doesn't kick off until the x squared term. So I know I'm going to have to differentiate a few more times. The third derivative, I'm now going to need to use chain rule for the minus 2 sine squared and for the 2 cos squared. And I can simplify a little bit. And this is a point when I would suggest, if you look back, maybe at just the previous line, maybe even go back to the line before that, or even the very first line. Are there any other ways of writing those expressions that might have made your life easier when it came to repeatedly differentiating them? For instance, the simplification I've done here for the third derivative is pretty obvious. We've got sine x cos x terms, so we can just put them together. But in the previous line, you've got a sine squared and you've got a cos squared. It might have made our lives a bit simpler if we'd replaced cos squared x with 1 minus sine squared and then grouped things together. Alternatively, you might recognize something else about sine squared minus cos squared, or you might spot it more easily with cos squared x minus sine squared x, and that will become more obvious if you look at the first derivative, 2 sine x cos x, which I'm hoping jumped out at a few of you as sine 2x. If you can write it as sine 2x, it actually trivializes most of the other derivatives that come after it, because sine 2x differentiates to 2 cos 2x, which in turn differentiates to minus 4 sine 2x, and so on and so forth. So it will speed things up quite a bit if you spot the double angles. You could have done that potentially right from the beginning with the sine squared by rewriting sine squared x in terms of the cos double angle formula. That feels a bit less obvious than noticing it when you get to the first derivative. and you won't lose much by jumping to the first derivative before you spot there's a double angle. But it's worth noticing. Now, I've done a few more of these because I'm doing it the long way in this particular case. I wanted to point out that the sixth derivative, which you can actually use this slightly weird notation for, I'm putting the power 6 in brackets to try to indicate that it's not f of f of f of f of f of f of x. It's the sixth derivative as opposed to composing the function by itself 6 times. But you might be able to see a connection between the second derivative, the fourth derivative, and the sixth derivative. And you can absolutely make use of patterns like that because as soon as you recognize that the fourth derivative is exactly -4 times the second derivative, you can differentiate twice by just multiplying by -4, and that will take you from the fourth to the sixth and so on. I suppose you could almost prove that with something like a proof by induction, but essentially if you take the second derivative and differentiate it twice, you'll get the second derivative of the second derivative. That's just the fourth derivative. So that pattern will hold, and you could quite easily continue that. You'll see a slightly more formal way of looking at that. Some other questions within the chapter focus on the idea of repeatedly differentiating a function, and just playing basically is the best way to explore, to play around with differentiating repeatedly and look for shortcuts that will speed up the process. For now, even if you did it the longest and least efficient way like I've done here, you can still work out your values: f of 0, f dashed of 0, f double dashed, f triple dashed, f quadruple dashed, and so on, all the way down to f sixth of 0. I have to go all that way because I'm looking for the first 3 non-zero terms. But once I've got them, I sub them in. You don't have to write it out quite as tediously as I have here. If it's a 0 term, just leave it off, but be careful to recognize which terms have numbers in. Don't just miss it out. Make sure you skip the entire x cubed section, for instance, and jump to -8 lots of x to the 4. Ultimately, this becomes x squared minus a third x to the 4 plus 2/45 x to the 6. That's the beginning of this expansion. And the third of our 3 examples, ln of x plus 1. We start by writing the function down. Remember that ln of something differentiates to 1 over the something, multiplied by the derivative of the something, but in this case that's just 1. To differentiate again, you want to think of it as x add 1 to the power of -1, so bring the power down in front, reduce the power by 1, gives you minus x add 1 to the -2. I'm going to go a step further because I can already tell what's going to happen with f of x. But of course, if you don't notice that you get zeros until after you start working out f of 0, f dash of 0, that's not a problem. Just come back and fill in a few more derivatives. But in this case, I've done them all at once. So once we've got enough, we can start subbing in 0. We get ln of 1, we get 1 over 1, we get -1 to the -2. 1 to the -2 is evaluated, and then you put a minus in front, so that's a -1. And the next one is a +2. That's enough for us to start completing our expression. Sub in those values to the general formula, and out it pops. X minus x squared over 2 plus x cubed over 3. What's quite nice about this is that if you go a term or two further, you'll see it's a pattern that continues. Because the powers of that x add 1 bracket, the -2, the -3, it's going to become -4, -5, they'll continue to be pulled down in front. That essentially gives you something which will cancel partially with the factorials from the function itself. As you'll see in a second, the general form for this, even if we go further than 3 terms, backs this up, that we end up with something that looks suspiciously similar to some of the others that we've seen, but instead of factorials, it's just the number itself, 2 and 3 instead of 2 factorial and 3 factorial. That cancelling is going to continue. It's worth asking the question, why did we go with ln of x plus 1 rather than just ln of x? Well, a nice way to think of it is to look at the graph. I've sketched here in black the graph of ln of x plus 1. It's the ln x graph translated to the left by 1 place. And maybe you can see what would happen if we go back, translate it to the right by 1 and get back to the regular ln x graph. Well, then we'd have an asymptote at the y-axis. And that's a problem if you're trying to evaluate the Maclaurin series expansion centered at x equals 0. And that's the way Maclaurin always works. As I say, Taylor series, you can adapt it, but it's essentially going to be a translated version of Maclaurin. But the Maclaurin series is always centered at x equals 0. And if the function does weird things at x equals 0, or even if some of its derivatives do weird things at x equals 0, then you would have a problem. That's why by translating this across, we can still get a function that behaves nicely and gives us a good approximation for the log function, but it's going to be a little different. If you want to use this to get an approximation for log of 2, for instance, you would have to set x equal to 1 rather than setting x equal to 2. And you probably have to go a few terms further to get a really accurate one. But it's going to be surprisingly good pretty quickly for values of x between plus and minus a half. In other words, for values of log of between a half and 1.5. So this is what you get in the formula book. At the beginning, you have the general Maclaurin series expansion in a format where you can just substitute in the values of f of 0, f dash of 0, and so on. You are also provided with the general expressions for the most common functions, e to the x, ln of 1 plus x, the one we've just done, sine of x, cos of x. They've also got arctan of x. You can and you may be asked to derive series expansions for some of the other inverse trig functions. It's worth exploring when you do the hyperbolic functions what the series expansions for sine and cosh and tanh would be. You can do tan as well. But these are the standard ones that are in the formula book. And sometimes when you're given a question, it's going to require you to just extract these and use them. So you can take assumed, for instance, the sine function and then use it to generate sine of 3x by replacing x with 3x all the way through. Or it might be that they ask you to prove one of these. So you know what you're trying to get it to, but you have to demonstrate why it works. And you would do that using the general formula at the top. The main things I want you to take away from this topic is firstly that almost any function can be rewritten as an infinite polynomial. We've seen already some edge cases where you might need to adjust the function. Maybe you've got to translate it so that you can still plug in x equals 0 without things breaking. But in general, any of the elementary functions you've encountered, including many that you haven't yet, you can use Maclaurin series for. It's a very powerful technique. The general formula you can derive by differentiating, and then you can use that to create your own Maclaurin series expansion for any weird and wonderful mixture and combination of functions. The third bullet point, series can be combined with one another. We've not touched on very much yet, but if you had, for instance, the series expansion for e to the x and the series expansion for cos x, you could put the you could multiply the two expansions together to get the series expansion for e to the x cos x. And obviously, multiplying two infinite polynomials together doesn't necessarily sound like it's going to be much fun. But you could, if you needed, for instance, just the first 3 terms, then you wouldn't necessarily need to deal with more than 3 terms from each of the 2 different expansions. And you can be a little bit savvy about which ones you ignore because the powers are so high that they become insignificant for small enough values of x. In terms of applications, you'll see this used when you're finding limits. Turning a function into its infinite polynomial form might allow you to cancel things out in ways that you wouldn't otherwise be able to. Approximating integrals is a common way of exploiting the ideas of Maclaurin series because, of course, if you've got a polynomial, you can definitely integrate it. And I'll put understanding functions as well, just in terms of seeing the connections between sine and cos and e to the x that we've done already. When we look at the hyperbolic functions sine and cosh, you'll be able to come back to the series expansions and compare them to the ones you've already seen and learn more about the function just by seeing what its DNA looks like. Now, there's a few questions I'd recommend you try from Corpio 2 exercise 2c. If you want some hints of how to begin with these, then you can watch the next couple of minutes of the video. If not, you're welcome to go away and crack on with them. I do have them up on the screen if you need them. Here's the first 2, and I'll put the next 2 up in a second. But we'll go through some hints for how to start with these if you've had a go and you want to come back and find out exactly what you should have been doing if you got stuck. So, spoiler alert, hints coming up for question 2. Use Maclaurin series and differentiation basically means you're going to do the kind of thing that we did earlier with sine squared and with e to the 2x and so on. You're going to take the function, in this case e to the sine x, and differentiate it over and over again. And then try subbing in 0 to the function's first derivative, the function's second derivative, and so on. You'll only need the first three in this case, I think, and you'll need a bit of chain rule and probably chain and product rule once you get to the next step. And then you'll be subbing numbers in and using that general formula from the formula book. Hints for question 7. You've been given a function which is already a messy combination of things. The first step is to find the second derivative. So you're going to need a mixture of product rule and chain rule to deal with that, because they're literally asking you to differentiate a couple of times. Keep track of not just your second, but also first derivative, because in part B, you'll need to work out the value of those various derivatives at 0. And you'll need to differentiate one more time for good measure and sub 0 into that as well. Once you've done that, it's asking you to express the function f of x in ascending powers of x up to and including the term in x cubed. That's just another way of saying give me the Maclaurin series expansion. So using your derivatives evaluated at 0, sub in to the formula from the formula book. Hints for question 9. You've been given the function, you've been asked to find the first derivative, and then for part B you'll need to find a few more derivatives and sub in 0. Then all you're doing is applying the Maclaurin series expansion formula as we've seen before. And then in part D, the first two terms of the series expansion, substitute x equals pi by 4, and you'll be able to do a little bit of rearranging. Notice that just like when we do this with binomial, we're using binomial for approximation, you've got to pay close attention to what's happening on the left-hand side and the right-hand side of your expansion equation. Because if you're only using the first few terms, the right-hand side will be an approximation to the left-hand side. You get an exact value when you sub things in into f of x itself. You get an approximation when you sub it into the series expansion. And for number 10, they haven't broken it down for you. They've just said, show that the Maclaurin series for tan is such and such. You're going to have to differentiate a bunch of times, sub in 0 to each one, and apply the formula. The last thing you can try, if you want, is exam questions taken from Corpio 2, Chapter 2, a variety of exam questions. These two have Maclaurin series expansion, one of them using it in order to approximate an integral, and the other one is using it to find an approximation for pi. So you get a combination of using your technique, but also seeing how it can be applied to things.